Hello, so in this lecture, we will talk about Matlab. So I will introduce some useful Matlab functions that you can use for solving the problem set in the lab session. So uh, so here I showed a Matlab software turned on in my machine, and you also have this Matlab software installed in your machine, and you will have somehow different layout of the windows within the Matlab software as shown here. So I have this text editor window and this command window, and these are the two windows that you need throughout this lab session. So when you have a new text editor like this, by pushing the button of the plus, then you always can create new text editor, and please do so, and please save this text editor wherever you want by pushing this button, save, and I will store this text editor in this folder, naming lab practice, and let's start. So first, we can create a variable like a is equal to 1, and if you run the code, then you will see the result like this, where it shows the stored value into this a variable. And when you add semicolon at the end of the line, and if you run, then you will not see any result. So here, semicolon is to mute the execution of this line. So although we execute this line and store the value into the variable, we don't see any printed result in this command window. And to wipe out the history of the command, we can type CRC, then and enter. Then all the history of the command window will be wiped out. And I usually do that in this code edit text editor, so that whenever I run this code like this, then I don't have any previous then whenever I run this code, then the previous history of the command window will be deleted. So, and then we can also create a vector variable like b is equal to 1, 2, 3, and let's run it. Then we have this row vector, and there is and let's mute this line, and there is another type of vector variable that is column vector. So if you type like 1 semicolon 2 semicolon and 3 and run it, then you will have this column vector. So to make a column vector instead of this row vector, you just need to include the semicolon between the elements of the vector. So if I delete this semicolon and run it, then we have this row vector and the column vector. And let's mute them by adding the semicolon at the end of the lines. And now let's talk about a matrix, a scalar matrix like A, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you run and you see this A matrix that is 3 by 3 square matrix. Then now it's time to learn how to do matrix multiplication. So in the classroom lecture, we learned how to do the matrix multiplication, right? So let's say we have A1x plus B1x, B1y plus C1g is equal to D1, and A2x B plus B2y plus C2g is equal to D2. Then we learned that this set of equation can be converted into the matrix multiplication like A1, B1, C1, and A2, B2, C2 times the coefficients x, y, z is equal to D1, D2, right? And the rule of thumb of this matrix multiplication is that when we write down the dimension of each matrix, then it looks like 2 times 3 and 3 times 1, and this is 2 times 1. And this the inner value between these two matrices should be the same, and this outer number will be the dimension of this resultant matrix shown here, right? So we will do this matrix multiplication in this Matlab software. Like, so A is 3 by 3 and C is 3 by 1. So if we multiply A times C is equal to B, but in software, the resultant value should be always on the left side, like this. And we can run the code and we see the result, right? So, and let's create another square matrix like B is equal to 10, 20, 30, 40, 50, 60, and 70, 80, 90. And let's learn it. And we have another new matrix. And let's unmute this line and run the code. Then we have these two square matrix. And there is a multiplication. So if we multiply these two matrices, and we have the result like this. Here, this 300 is coming from multiplying this first row of this A matrix and the first column of this B matrix, so that by adding them up, all the element-wise multiplication between this first row and the first column, we have this 300, right? Then there is another type of matrix multiplication, that is element-wise multiplication, that can be done by adding a period in front of the multiplication operator, asterisk, like this. And if we run this, then this matrix, which is out of this line, is coming from the element-wise matrix multiplication of A and B, for example. So let's mute this one and run this code again. Then this matrix is coming from this line, A period and asterisk B, and that is coming. So the first column is out of multiplying this first element and the first element of A and B respectively, and this variable, this element is coming from multiplying this element and this element. So yeah, so this is the basic of the Matlab language, like variable types like scalar, row vector, and column vector, and the square matrix, and the operation of those matrices, like uh, the, the the regular matrix multiplication and the element-wise matrix multiplication. Then I wrote double percentage symbols, and by that line we can divide the text editor into different sections like this. And I will here, let's say I want to declare a P matrix, which is 1, 2, 3, and 4, 5, 6, and 7, 8, 9. And if I want to run only this section, the bottom section, then we can push this button, run section. Then only T matrix, this line is executed. So the previous history of the text the command window are not deleted because CRC is not executed. So let's add here CRC and run this section. Then the previous history is gone and this T matrix is declared here, right? And I will now introduce the function spdix. So we have the column vector C, and I will introduce how to create a diagonal matrix. So we learn, yeah. So let's just work on the Matlab. So if you type like C and at 0 and 3 by 3, so, and let's run this code. And you have so let's run again. Then you have C vector, which is defined as 1, 2, 3 in a column vector format. And by this line, we just created a diagonal square matrix where the center diagonal line is filled with the elements of this C column vector. And the language is like this. So here C is the column vector that contains the values for these diagonal lines. And here 0 indicates this center diagonal line. And what if we have C the same line, but here we just have -1. And let's run this code. And I will delete C here. And this diagonal matrix is coming from the previous code here, and the new line of code creates a diagonal matrix, but the non-zero diagonal line 1, 2 is one step off diagonal from the center line to the left side. See, and if we have another code where we use +1, then the resultant matrix looks like this, where this C column vector is located on the one step off diagonal line to the right hand side like this. And here you need to remember that the end member of the C column vector is omitted in this square matrix. And in this matrix, the first element of the C column vector is omitted. Okay, and this spdix function is the essential function to construct the transmissibility matrix. So, for example, let's write down a new line of code like C and another C here, and -1 and 0. Okay, and I will mute the other lines. And let's run this code. And we have then tri-diagonal square matrix where this center line is corresponding to this C and this index 0, and this 1, 2 one step off diagonal line is corresponding to this C vector, and here -1. And this one step off diagonal line to the right hand side is corresponding to this C column and this index 1. Okay. Then now we are all done for the basics of Matlab. Now let's look at the problem set that we need to uh, write some code. Okay. So let's turn, where is the problems? I will open the problem set file. That is, where is it? Yeah, so this is the problem set. So here, this is a one-dimensional groundwater system where the left boundary is imposed by this influx boundary condition, and the right-hand side boundary is imposed by this head boundary condition. And then the other constants given in this preset is that we have this hydraulic conductivity and the domain size is 1 meter. And you are asked to write down the code to solve the head distribution in this one-dimensional groundwater system. So let's here declare the given constants like the hydraulic conductivity, which was so it is 10 centimeter per second. So in meter scale, it is 0.1 meter per second. Okay, and we also have the domain size as long as 1 meter, and we have flux boundary that is 1 centimeter, which is 0.1 meter per second, and we also have head boundary, which is 1 meter, right? So we declared all given constants in the P set. And then now let's discretize the one-dimensional groundwater system. So first, let's declare a n variable, which is the number of grid cells within the system. And I here will use value 5, which means I will discretize the one-dimensional system into 5 segments. Then the cell size will be estimated like L by 5, right? And I need to create the vector of the cell hydraulic conductivity and I will use this function once and by 1. So here once, this function once like 3 by 3 create a 3 by 3 square matrix where all elements are 1. And if I create like 3 by 1, then it will create a column vector with all elements to be 1. Okay, so if I define the kx variable like once n by 1 times k, then it will, and let's run this, then it will create the vector of hydraulic conductivity where each element is corresponding to the cell hydraulic conductivity. And because we have 5 grid cells, we have 5 hydraulic conductivity values. Okay. Then let's define the hydraulic, the transmissibility. Here, transmissibility is defined on the cell interfaces, right? And we have 2 types of cell interfaces. One is the left cell interface, and the other one is right-hand side interface, right? So we will have T So TL will be like 2 over dx. We covered this in the classroom lecture, right? So times 1 over kx from the first cell to the second to the last cell by m minus 1. And then we have kx from second to the last cell, right? And please be able to relate this indices to the I minus 1, and this indices to I, the indices I, and this should be to the minus 1, right? And all the operations should be done with elemental wise, so that we here added these period symbols, right? And let's run this code, and we have the transmissibility values on the left-hand side cell interface, and likewise we can also create the right-hand side transmissibility 2 over dx times 1 divided by kx from second to n. So here I would say this is tx, right? So here I have 4 elements of the cell interfaces transmissibility. So let's run again then, and I have this here, the tx, and now it's time to define tl. And if you look at the boundary condition on the left-hand side, the inlet boundary is defined by the flux boundary. So we don't have to have the transmissibility value on the inlet interface. So we will use 0 value on that interface. So we have Tx. Okay, let's run this, and we have now TL transmissibility, and likewise we have TL. Here we have, so before create this TL vector, let's first think about TL at n. So here this variable indicates the transmissibility at the outlet interface, and we learned in the classroom that this should be defined as 2 over delta x times minus 1 over kx at the last cell plus 0 to minus 1, right? And let's run this, and we have this variable should be 1. And now it's time to declare the right-hand side of the cell interface transmissibility vector, which can be defined as Tx over Trn, right? And let's run this code. And now it's ready to, so we now have defined the transmissibility on the left-hand side cell interface and the right-hand side cell interface. And we also need to create a TC transmissibility, which is the summation of the TL and TR, right? TL, TR. And let's run this code. And now we have created TC2, okay? And let's mute them. And let's create the transmissibility matrix, TMAT, using the SP diodes. So it is minus T R, and TC and minus TC, which will be located at the one step off diagonal to the left and at the center line, and one step off diagonal to the right hand side, and the size of the dimension of the transmissibility matrix should be m by n. And this is the transmissibility matrix that we should estimate. And now let's define the unknown, the right hand side column vector, which should be zeros for most of the elements, right? And that can be defined using this function zeros, like m by 1. So if you declare like 3 by 3, then you will have a zero matrix of 3 by 3 dimension. And if you run this line, pushing this button, then we create this 5 by 1 column vector where all elements are zero. But we should replace this first element and second element, honoring the boundary conditions, right? So B1, so we learned that the first element of the right hand side column vector should be the influx boundary condition, right? Q bar, and the last element should be P, the transmissibility of the outflux interface, which is TRN times the head boundary condition H bar, right? So it is. So let's run this code and let's check the B. And this is unknown. This is the right hand side column vector. Now we can estimate the unknown head vector, like using T backslash B, right? So if we run this code, then we have, so T should be met, right? Let's run this. So this is, there is something wrong. There is something wrong here. So let's check. So let's check the T-man matrix. Here it looks good. Oh yeah, here it should be R, not C. Okay, and we have these head values, right? And the H bar is 1. Okay. So here I had a typo here. It should be L. And let's run this code again. Then we have this numerical solution of the head distribution. Okay. So now you learned all necessary languages or functions of Matlab to solve the problem set. Thank you.